Okay.
Okay, are you able to see this?
Yeah, we see it perfectly well. So please, you can start. You have 25 minutes and 5 minutes. Please keep for questions. Okay,
Okay,
please.
okay, okay. Good afternoon, all of you. Myself, Zalak Shah. First of all, I am very much thankful to the organizer committee of this international workshop on high energy physics to give me a chance to present my work here. My presentation is on properties of doubly heavy baryons, and today in India we have the special festival called Diwali. So from my side, happy Diwali to all of you and have a prosperous new year ahead. And this work is in collaboration with Dr. Ajay Kumar Rai, SVNIT Surat, and we have published paper on doubly heavy baryons. First is EPJC 2016, and it is based on the doubly heavy omega baryons, and the another is EPJC 2017, which is on doubly heavy cascade baryon family. Okay, so this is the outline of my talk. After the brief introduction, I will give the introduction to our model, which is the hypercentral constituent quark models. We discuss our model, then to the doubly heavy baryons. In doubly heavy baryons, we see the mass spectra, and then the Regge trajectories and the magnetic moments of this doubly heavy baryon family, followed by the light baryons, nucleons, and star and delta baryons, which we are currently working on, followed by the closer. So when we talk about the baryons, it always starts with the standard model. I will give the quick review of the standard model. So particle physics is study on the matter and force that you all know, the elemental fundamental elementary particles and the interaction between the elementary particles conducted by the force. So this is the photo of the standard model. We have 6 quarks and 6 leptons and their antiparticles, which are interacted by the gluons, photons, and WZ bosons, which are the force particles of the strong interaction, electromagnetic interaction, and weak interaction. People now working on beyond the standard model, and they are finding the anomalies of the RK and RK star as etc. But here we're talking about, when we're talking about the doubly heavy baryons, it is important to go through the spectra once. So for the standard model, we have bosons and fermions. And when we're talking about the baryons, they are fermions, half spin particle, antisymmetric, and which follows the Fermi-Dirac statistics with half spin particle. So for the baryons, we have light sector, light heavy sector, and heavy sector. Mesons, we have light sector, light heavy sector, heavy sectors, and now people are more working on the exotic states, globalls, tetra, penta, hexaquarks, the diquark, dibaryon quarks, molecular states, etc. Now people are working on this exotic states. Okay, this workshop is based on the QCD, so there is no point to discuss QCD here, but this is just introduction 1 and 2 slide for the input of the QCD here. So the interaction is governed by the massless spin particles, which are the gluons, and we know that main two terms for this is asymptotic freedom and the confinement. So we are considering these two conditions for that. Now for the theoretical background, an essential requirement for the progress of in hadronic physics is full of usage of presence facility in development the new ones, with a clear focus on experiment that provide a genuine insight into the inner working of the QCD. So I have listed some of these review articles, which is very helpful to study the background of this hadronic states. So we can, these are the review articles which will help us to find from beginning to the excited states. So here is the list. Next is The spectroscopy of heavy flavor hadrons has attracted considerable interest in recent years due to the many experimental facilities. The facilities are Cleo, Baba, Bellet, Avatron, Zalak, CERN, and the future experiments Panda probably for the only for the charm sectors because it has a 5 GeV limit, Bell 2. Now the interesting thing is LHCb is giving many more results after the 2016 or 17. In 2016, we have started calculating the spectra of singly heavy baryon, then the doubly and the triply heavy baryon. After that, we get many excited states. Ground states are known. Most of the ground states are known to us, but many excited states has been provided by the LHCb, starting with the omega C baryons. 5 excited states of the p states has been given by the omega LHCb. Then the in the bottom sectors in last 1 and 2 year and in current year also we have many results for lambda b baryon, sigma b baryon, cascade b baryons, and cascade c baryons. Bell 2 has also given the results for the omega b baryons and omega c baryons. So this is very helpful for the theoretical people like us to give the resonance and the will get the experimental results which are in that particular resonances. In search for the light resonance is the main focus on the baryon program. These are the baryon program for the light baryon and the list is given below. Okay, now the model. Different approaches. The excited states of the nucleon have been studied experimentally from 1950s. I have listed some of the approaches which had worked on the doubly heavy baryon masses. So which has extracted the ground state, and some of them have extracted the excited state masses of the doubly heavy baryons. Starting with the relativistic quark model, Ebert et al. They have given the spectroscopy for the light, for the Cham bottom baryon. In the paper is from 2002. Then the variational approach by the Roberts, they have given the excited state masses up to 2p and 3d status. Then the Faddeev approach, which was given by the Welkers. Lattice QCD approach. For the lattice QCD approach, we Padmanath et al. They have paper in I guess 2016 or 17. After paper they have published that, and for those paper they have given the spectra up to 7/2 plus JP value and 7/2 minus JP value, and they have given the energies value with the approach of the lattice QCD. Then we have the Hamilton model, which is 2015 paper, recent Regge phenomenology paper in 2017 and the another is 2018 paper. They have given the spectroscopy of the singly, doubly, and triply heavy baryon. Very important is our next speaker, Professor K. Azizi. They have recent paper on 5th November, which is based on the dense medium. They have taken the approach and determined for the 3/2 parity values. They have one more paper on 2019 when they have discussed 1/2 parity value, and previous paper they have considered the QCD sum rule, then diquark picture and chiral model. So these are the models. Some of them given the excited state mass. Brown, Paula, all have given for the only for the ground state mass. But my question here is that after the discovery of the cascade CC baryon in by the LHCb, they have given the mass of 3620 at the ground state with the parity 1/2 plus. Before that, in 2005-2002, Zalak has given this masses as 3520. So there is 100 MeV mass difference between those two results, and due to that, many theoretical approaches have recalculated the mass spectroscopy with the same approach and the decay properties, and they revisited the spectrum. Now the interesting thing is that after the revisit of this spectra, we can easily found the 200 MeV difference for the excited states. As we know that when we move from ground state to the excited states, the energy value will be increased. So due to this difference of the 100 MeV, the new results, which is from diquark picture and chiral quark model, and some rules picture Huazing Chen and et al. Their paper, I can easily found there is a 200 MeV mass difference of their new mass with our approaches, which has been published in 2016 and 17. So this is one of my questions which I want to know. Now, focusing on our model, which is the hypercentral constituent quark model, I want to like to share that we have using the Jacobi coordinates, and which is confining three body potential and in the string like picture, and uh, the quarks are connected in the gluonic string, and the radius and their angle are shown as in this equation. The hyperradius x is the collective coordinate. So when we are doing the hypercentral approximation, we have the v of r j is equal to v of x plus some order correction. So it is defined on the hyperradius v of x, and it also contains the three body effect. So the Hamiltonian of a system can be expressed as x is equal to px squared by 12. It means the kinetic energy term and the potential energy term. Now the hyperradial Schrodinger equation, six-dimensional hyper-Schrodinger equation, is reduced in this form. You can easily observe that this is the angular momentum term L into L plus 1, which is converted to here. Now for the potential term, we have potential like that. We have added the first order correction to the potential, which is v of v1x. Here the tau is hypercoulomb strength, and the beta is spring tension, and these are the Casimir charges, and alpha s is the spring coupling constant that we all know. And for the spin dependent part, we have spin term, spin tensor term, and the tensor term. So for that, this is for the determination of the spin singlet and triplet splittings, and this is for the fine structure, and these two terms are for the fine structure. Now coming to the doubly heavy baryons. So this is the schematic diagram for the doubly heavy baryons, and this is the ground state. Those are the light states that we all know that we have 4 deltas, 3 sigmas, and 2 cascade and 1 omega. When we move to the ground state to the upper higher energy state, we can see that one strange quark is replaced by one heavy quark. So on the first floor we have singly heavy baryons. On the second floor we have doubly heavy baryons. At the topmost floor we have the triply heavy baryons. This is the decoupled, and this is for the octet. So this is the list of the singly heavy baryons. We have 7 members, and same 7 for the bottom sector as well. For the doubly heavy baryons, we have 2 families, omega family, in which we have 3 particles, CC, BB, and BC. And for the cascade family, we have 6 particles. Excuse me. And for the triple heavy baryons, we have 4 particles. Now the 2 heavy quarks.
So are you okay? Everything's fine? Are you okay? We cannot hear you.
Can you hear me?
Yeah. Are you okay? Everything's
I'm really very sorry. No, I'm fine.
Okay. Oh, so it's all fine. So, but you just not share now. Yeah. We can see your desktop. Probably open your presentation once again.
Can you see?
Okay, it's perfect. Yeah.
Give me 2 minutes for water. Okay, sorry. So now we start. The 2 heavy quark combination is CC, BB, and BB, and BC. And this for the doubly heavy baryons. Omega baryons, the strange rays is -1 and isospin is 0. So while for the 6 doubly heavy cascade baryons, light baryons, we have U and D quark with the combination with the S quark. So the mass difference of U and D quark in our model is only 12 MeV. So it is very obvious that when we move to the excited state spectra, it means from the S state to P state to D state to F state, we can easily see that this difference would be less than 10 MeV. So for the completeness of this work, we have calculated all 6 members of the families, and we have calculated the whole spectrum. But this thing is also mentioned by M. Carlinier in their PhD paper in 2015. So when we are taking the isospin splittings of the two baryons, and when we move to the excited state, we can find that the energy difference is very much less than 10 MeV. And that we can also found from our spectroscopy results. Now the calculation have implemented for the ground state, and ground state we have 1 by 2 plus and 3 by 2 plus parity. Then the radial excited state, that is for 2s to 5s, and the orbital excited state 1p to 5p. Now we have considered the all isospin splittings for this our calculations. For we can say that for p state we have 5 combinations: 1 by 2, 1 by 2, 1 by 2, 3 by 2. Then 3 by 2, 1 by 2, 3 by 2, 3 by 2, and 3 by 2, 5 by 2. For the D states, we have 6 combinations. So those combinations are 1 by 2, 3 by 2, 1 by 2, 5 by 2. And then 3 by 2, 1 by 2, 3 by 2, 3 by 2, 3 by 2, 5 by 2. For the F states, we also have 1 by 2, 1 by 2, 1 by 2, 3 by 2. The parity would be different. For D, it is plus, and for F state, it would be minus. So 3 by 2, 3 by 2, 3 by 2, 5 by 2, 3 by 2, 7 by 2, and 3 by 2, 9 by 2. So these are the combinations for the all spectrum. We have not shown all the result and all the combination here. We only show, I have only show those results which have been calculated by other theoretical approaches for the simple classification and for the simple names. Now, when we start about the ground state, as I have mentioned earlier, select experiments has already given, and then we have LHCb. So for the ground state and the excited state of the doubly heavy baryons, these are for the cascade BB baryon, and this is for the cascade BC baryons.
Sorry, we cannot hear you now. It's your microphone is. If you want to unmute, you can unmute yourself. Yeah. Are you okay? So everything right? Yeah.
Yes.
Okay. So. Yeah, you can take time. I mean, a minute to drink your water. I mean, if needed, of course. Sure, it's not a problem. So.
Okay, so for the omega CC baryon, I think its microphone is on. Yeah. So for the omega CC baryon, we can easily find that 2s to 5 state, the authors of their other, it means the 6, 10, 11, 12, 9, 5. These are the this is the Ebert's result, and this is the result of the Roberts et al. And this is the other result. So you can find that for the 2s state and the 3s state, you can find that here the other predictions has, which is 6.714, and our is 6.3147. So my point is, there is a vast difference between the results of the theoretical models. So it is very much important to get the experimental opinions so we can find that the actual resonances of this baryons. Now, for the spectra of the omega BB baryon, it is quite impressive that for the heavy sector, it means from the jump sector go to the bottom sector, we can find that this can be found in the range with the other predictions. So we can expect that it is between the 10.61600 to 10.700 and something. So range can be predicted. Now for the case of the omega BC baryons, the diquark baryon model has in theory they can state that the excited states are not possible due to the emission of the soft gluons, because they are taking the diquark picture. And for in the case of the diquark picture, when we are considering the BC, the emission of the soft due to the emission of the soft gluons, they cannot they cannot find the excited state for the omega BC. So there is a rare study for the omega BC, and we have calculated those results. And this is one article from the PID. They have also calculated for excited state. The rest of the day, I could not find any results for the omega BC till now. Same way for the radial excited state for the cascade baryons, thus we can find that we have calculated from 2s to 5s, and for the cascade BB as well, cascade BC as well. The references are given and they are according with each other in case of the cascade CC. This is the orbital excited states for the omega CC baryons. Now we do not have given the whole spectrum here, because it is quite inappropriate to find the perfect results through the slides. So we mention only those results which are calculated by the others approaches as well. So in case of this cascade omega CC baryons, uh, the results can be found in accordance. But in case of omega BB, there is a vast difference, as I have also mentioned earlier in case of the ground states. The same way, this is the results for the cascade baryons. For the both isospin splittings, you can find that here it is 3.853, this is here it is 3.846. So you can find that the difference is very small. But for the completeness, we have shown this slides. Same for the omega cascade BB. Now, the Regge trajectories. So Regge trajectory has a very important topic, and it is a very successful in fundamental theory of strong interaction at a very high energy is still in discipline. So for the Regge trajectories, we plot two graphs. One is m square versus principal quantum number n, and the another is m square versus the angular quantum number. For angular quantum number, we take two graphs. So, and this you can find in our next slides. So obtained masses are plotted in accordance with the quantum number with natural and unnatural properties, and you can find that the linearity, divergence, and parallelism. That's what we have to find. So while we find the intercepts b0, alpha 0, beta 0, and slopes beta and alpha, by using those intercepts and slopes, we can put those values and find the unknown quantum number. So it is very effective and very important tool to find the parallelism as well as the linearity and to determine the unknown quantum number. So it is very important thing. Here you can find that, as I have stated, there are three trajectories. One is here and the rest are here. So for the J, in the natural parity, we take 1 by 2 plus 3 by 2 minus 1 by 2 plus it state for the S state, 3 by 2 minus for the P state, 5 by 2 plus for the D state, and 7 by 2 minus for the F state. This is the natural parity. And for the unnatural parity, you can find the 3 by 2 plus again for the S state, 5 by 2 minus P state, and 7 by 2 plus is D state, and n by 2 minus is the F state. So some of the trajectories are shown here for the completeness. Using the slope and interaction, slopes and intercepts, we can also find the quantum numbers and determine the JP values in our conclusion section. Same type the rigid trajectory for omega baryons. Now the next is magnetic moment. So electromagnetic interaction are important to examine the structure of the heavy baryons, and many theoretical studies have calculated the magnetic moments for the ground states. Recently in recent paper I have in 2020 May, I guess, it is published on EPGA. They have also considered and calculated the electromagnetic transitions and electromagnetic moments of the ground state of all these 9 baryons, 6 from the cascade family and 3 from the omega baryons family. But my another question here is, for the magnetic moment, we have now we are getting an, these are the previous study before we have done, we are getting the results for the ground state, but we do not have any results for the excited state. For the excited state, I think I have read somewhere that it is mentioned that it is a combination of 2 quarks and 1 light quark. So the light quark plays a crucial role for this electromagnetic interactions, and due to that we could not able to determine this excited state magnetic moment theory. So I would love to know from other experts that if there any technique or if there any experimental possibilities or if there any theoretical technique to determine the magnetic moment of this heavy excited states. It means the PD and P states, excited states, magnetic moment. If it is possible, please let me know. And the study has been performed. We have performed for all singly, doubly, and triply heavy baryons. And this is the approach what we have done from the hypercentral constituent quark model. We have this equation, and the effective mass is written as like this, which is given in this equation, and E plus V spin. So for the magnetic moments, spin flavor wave function 1 by 2 plus, we have 9 baryons. The function is already given, which we have found from the book, and this is our result, which are very good. We are in good accordance with the other predictions till now, which we have find for the uh, electromagnetic transition in the magnetic moments. Now for the magnetic moments, spin favor function 3 by 2 plus. It means like S state, radiative, etc. 3 by 2 plus. Now I want to show the last 2 slides for the recent work, and that is for the nucleons. For the nucleons, we have neutron, proton, and delta resonances, which are nucleons, and hyperons. We know that we have delta, sigma, cascade, and omega. This is the diagram, which were the ground states of the previous heavy quark diagram. So this is known to me. Now for the light baryon spectrum, we have implemented the same theoretical model, the hypercentral constituent quark model, to the this light baryon spectrum, and you can find here that easily they are apart from the this 1 by 2 1D state, 3 by 2 plus, and that 5 by 2 state, 1 2D state, and 1F state of this 7 by 2 minus, all are in accordance with the experimental resonance state. So this is the spectra of the N baryon. Similar spectra for the delta baryon. For the delta baryon, some of the resonances are shown in the form of the Regge trajectory, and here we have done 3 by 2 plus. For the delta resonance, we have 3 by 2 plus only, and for the N baryons, we have 1 by 2 plus. And for P, D, and F state, we take 1 by 2 minus, 5 by 2 plus, and 7 by 2 plus parities, and we determine these values. So with this, um, the closure in closure, we have I have present the baryons containing 2 heavy quarks, which are the chang chang bottom and chan bottom, as well as the light baryon quark, and the excited states of this doubly heavy baryons and their magnetic moments and the Regge trajectory are also determined using the hypercentral constituent quark model. I am very much looking for the new results from the future experiments so that we can compare, and we have the excited state mass spectroscopy as well in the doubly and triply heavy baryon as we are having right now in the singly heavy baryons. Thank you.
Okay, thanks a lot for your talk. So yeah, especially that thanks a lot for giving it, especially that it seems you have a cold. So like I wish you health. So
Yeah, due to the weather change,
yeah,
the
yes.
winter is started, so I'm really very sorry for this.
No, not to be sorry. What I mean, thanks a lot for agreement for your agreement to give it anyway. So it was a heroic, I mean, gesture. So we will have a discussion session. I mean, but it will be quite late in the evening. Probably we have some time for questions now. You can raise your hands, and I can see that Anatoly Rikhadet is with us now, and all the problems are solved, right? Anatoly, can you hear us?
I have only one question. What's the slope in the Regge trajectory for double heavy, and light baryons? The same or not?
No, they are different. We plot in
You show us the Regge trajectory. This Regge trajectory have a so famous slope. The slope have to be the same as in from meson, for example. But my question about slope for different type of baryons, is slope the same or different?
No, they are different. We have also determined the slope and intersects, and can I show the values of the slopes and intersects right now? I have a paper right now, so I can show you
Okay.
if you need.
Okay. Thank you very much.